Greetings, pre-calc students. This is Mrs. D, here to give you a few lessons about acute angle trigonometry. Now, if you notice on the handout, your notes, I accidentally started writing acute triangle trig, and I realized that was a little bit of a mistake because none of this is valid actually unless we have a right triangle. It has to be a right triangle. Of course, it will have two acute angles in it, but it must be right triangles that we're dealing with for all of these trig ratios. There's three goals today. One is to describe all 6 ratios for any angle. Yes, I said 6 ratios. There are more than just the 3. I also want you to be able to find exact ratios for certain special angles. That will be exact radical form for these numbers, not decimals. Please don't use your calculator for those. And lastly, understanding and recognizing the difference between ratios and radians. They both start with an R and an A, but there's definitely a difference between a ratio and a radian measure, although both will sometimes be presented in fractional form. To start with here, we're going to define ratio as a comparison of two quantities by division. So when we look at this here right triangle, we only have 2 given sides, and at this very moment you might say to yourself, well, there are only 2 ratios we could write, 5 to 13 or 13 to 5. Now what are those 2 ratios in particular in this triangle? 5 to 13 might be the sine ratio for angle beta, the opposite side compared to the hypotenuse side, and 13/5, well, that's comparing 2 quantities, but maybe we don't have a name for that yet. Notice I said yet. Now, of course, a person could use Pythagorean's theorem and solve for the third side and realize that b is 12. And that opens up the window for possibilities. We can write other ratios now. We could, of course, say 5/12 or 12/5. Also, we could write a ratio that involves 13 and 12. So 13/12 and 12/13. With these 3 measures, these are the 6 different ratios we could be writing. It's my understanding that coming into this class, you probably have knowledge of the sine ratio, possibly a cosine ratio, and a tangent ratio. Well, these others have names as well. So 5/12, let's just give that a name. 5/12 might be what we call tangent of beta. We should know that right now. And cosine, where do we have a cosine ratio? How about here? 12/13 is the cosine ratio for angle beta. So these 3 names are pretty well established in your prior knowledge, I think. You know what sine, cosine, and tangent are. We do have other ratios, of course, and these other ratios also have names. Some new vocabulary for you here. If 5/12 is the tangent of beta, then 12/15 is what we call the cotangent of beta. This is a reciprocal ratio, defined in your notes there by the adjacent side compared to the opposite side. Now definitely order matters there. If you divide 12 by 5, you get a very different value than if you divide 5 by 12. But this is the cotangent ratio. For this particular angle, for any angle, it would be the adjacent side compared to the opposite side. We have 13/12, which is the reciprocal of the cosine ratio that is called secant. Again, that's a reciprocal ratio defined by the hypotenuse side compared to the adjacent. So we're kind of covering all of our bases here, describing every single possible ratio. And 13/5 is what we call the cosecant of angle beta. The reciprocal of sine is cosecant. That would be the hypotenuse side compared to the opposite side in that order. Now it's going to take a little getting used to here. A lot of people confuse secant and cosecant. But if you just kind of use similar structure in your practice, You'll get them down. We have all 6 ratios defined here. Of course, we could find these ratios also for angle theta. Theta is also a popular Greek letter that gets used for an unknown angle. But in this scenario, we just kind of focused on angle beta. Okay, let's see how you do here, understanding that all of these ratios can compare the sides of a triangle. And notice that these reciprocal ratios, all of them actually in this example, are unique. Maybe to your experience, you've never seen ratios written like this because you're not used to these numbers being in excess of 1. But all 3 of these actually are numbers larger than 1. So get used to that. It can happen. It just did. Now here's your first example to maybe try on your own, or to work along with me here. You can pause if you'd like to try to write the 6 ratios for angle theta. Here's theta. And so perspective matters here relative to this angle. Sine of angle theta has a certain value, cosine of theta. All of these are ratios that hopefully you're familiar with. And then for me, when I set up this structure, I like to kind of repeat my practice and be organized here. Cosecant is the ratio I'll find next, and hopefully that's a reciprocal value of that sine ratio. Secant likewise, I like to find that next because that's the reciprocal of the cosine ratio. And lastly, cotangent is the reciprocal of the tangent ratio, whatever that might be. Now 8 and 10 are given, which means at this very moment I could write the cosine ratio as 8/10, which I'd like to simplify that. How about 4/5? And that means the secant ratio compares the hypotenuse here to the adjacent, saved it, and that means that ratio is 5/4. Without having the opposite side, it's kind of challenging to come up with the sine ratio, also to come up with the tangent ratio. So I'm going to do a little Pythagorean theorem here. That gets used a lot in this trig, especially because we're dealing with right triangles. I'm going to subtract 64 from 100. 80 squared is 36. You've done Pythagorean theorem probably in your sleep. So the missing side there is 6. Now I can write my other ratios. 6/10 for sine would be 3/5 equivalent, and that means the cosecant ratio is 5/3. So we're just comparing sides here, looking at the relationship between them. And last but not least, tangent ratio is the opposite side compared to the adjacent side. So 6 to 8 reduces to 3 to 4, which means the cotangent ratio is the adjacent to the opposite, or 4 to 3 in simplest terms. 4 to 3. Okay? So, I do want you to write what each ratio is, like give it its name. Please don't just write a bunch of fractions down and say, hey, I found them all. Pokemon, catch them all. No, you're just going to name every ratio. This is the tangent ratio. This is the cotangent ratio, and on and on. Now in this example, it feels like there's maybe not enough given information, but you're supposed to find the remaining 5 trig ratios. Now without doing any additional calculation, I hope you can find the tangent ratio for angle A, knowing the cotangent ratio is 3. The tangent of A is the reciprocal of that value. The reciprocal of 3 is 1 to 3, or 1/3. And then you feel stuck. Helps maybe to draw a picture. So I'm going to visualize angle A here in a right triangle. Angle A is some acute angle. I'm never going to find it. I mean, you might want to. You're probably tempted to find tangent inverse of 1/3, but that's not necessary. Nonetheless, I'm actually going to move angle A to make it more accurate to this given information. There we go. Let's call that angle A. And I'm going to label the sides. Opposite is 1, adjacent is 3. We could have also done that from the given. Knowing the ratio for cotangent, we have the adjacent side compared to the opposite, which also tells us the same information. Basically, we have a 3 to 1 side comparison. There's the 3, there's the 1. knowing the third side is square root of 10 would allow us to write all of the ratios, not just tangent, but also, sine and cosine for angle A. That's another thing. Please write the angle. Even if it's unknown, these functions are meaningless without an angle input. So sine of A, for example, is 1 over the square root of 10. And we need to practice writing this in simplest radical form because that's how we're going to move forward here. That would be square root of 10 over 10 after multiplying numerator and denominator by square root of 10. We also have cosine here. We can write that as the adjacent compared to the hypotenuse. Again, rationalizing that denominator. 3 square roots of 10 over 10 would be the simplest radical form. And we are missing how many ratios? We have 1, 2, 3, 4, 5. We're missing 2 more. So cosecant. Cosecant. Yes, I can. Cosecant is just the square root of 10 compared to 1. Or we could just write the square root of 10. And secant of angle A is square root of 10 compared to 3. Hypotenuse compared to adjacent. And there you have it. One little piece of information. After drawing a picture, we found all the sides, and therefore we could write all of the ratios, comparing them. Now the next thing we're going to go into here is what we call the special right triangles, and I'm sure you've been exposed to these in geometry, but we're really going to take this to the nth degree in pre-calc. This 30, 60, 90 triangle, I'm going to show you how it's derived from an equilateral triangle by dropping a perpendicular bisector here. Perpendicular, forming a right angle, and I know it's a bisector because all of these sides are the same, remember? And so that symmetry is kind of inevitable when we bisect that angle. We're also bisecting that side. So there's our 30-degree angle because a equilateral triangle has all 60-degree angles. And there's another one of them right there. Now the sides are all related here. They're all the same to begin with, and I'm cleverly choosing to call all of these sides 2x, which means that this side here of my 30, 60, 90 is just half of that, or x. Now by way of Pythagorean theorem, we can find the third side. Usually that's the one people have a hard time remembering, but so far we have x and 2x. There's a 1 to 2 relationship here between that short leg and the hypotenuse. And I am going to call that the short leg, not to discriminate, but because it is. It's the shortest leg because it's across from the smallest angle. And finding that third side, I'm going to use Pythagorean's theorem with these arbitrary values. So x squared plus we don't know squared equals 2x squared. Careful there, 2x times itself is 4x squared. And now I'm solving for that third unknown side so that I can figure out how it's related to all the other sides. So this question mark squared is 3x squared. And that means if I square root, that third side is x times the square root of 3. So these are how the three sides are related every time in a 30, 60, 90 triangle, and this will prove to be very useful if I ask you to find one of the ratios for a 30, 60, or 90 degree angle. So again, I'm going to label that here, x times the square root of 3. This is what I call the long leg. It's not the longest, obviously the hypotenuse is longest, but think about that number 2. The whole number 2 is bigger than the square root of 3. The square root of 3 is approximately what, 1.8, 1.6, something in there. So all of these sides, however, are related to this short side. And because they are all comparable here, we should be able to find ratios even if we don't have a specific measure. One other note, this is called the 30, 60, 90 triangle. Also known in the radian world, we're going to translate this to pi over 6, pi over 3, pi over 2 triangle. Yeah, that's what I'm talking about. 30, 60, 90 is the pi over 6, pi over 3, pi over 2 triangle. That's, again, in the world of radians. These are the same special angles, just in radian measure. Our last special triangle here